Hi everybody, welcome back to the channel. In this video we're going to take a look at a proof of the fundamental theorem of calculus, or at least the first part of the fundamental theorem of calculus. To do this you'll need to make sure that you know the results that are in the last video. So if you haven't gone and checked out that last video that has 3 different results to take a look at, go check that out first because those will all be helpful when we look at this proof. Okay, the statement is up above. Let's just go ahead and jump right in. It says if x is continuous on a closed interval from a to b, then we can define a function g as an integral from a up to x. I want to start out by kind of looking at a picture that illustrates this interval, and so we'll have a here and b here, and the closed interval that we're looking at says that x has to be between a and b, so x is somewhere in there. X could be one of the endpoints, but we're not too worried about that case. Let's put x in the middle here. And notice that we're defining g as an integral from a up to wherever x is. Now, for the sake of this problem, I'm going to use f as a positive function, and this is our t-axis, not our x-axis, because x is going to be a value that's changing here. T is our input, but when you think of integral, you should think about this is f is talking, or I should say g here, the integral is talking about the area from a up to x. Okay, that's how we're defining this new function g. And what we're going to kind of focus on is the part here that says g prime of x is supposed to be equal to f of x. So let me give you a little bit of structure first, and then we'll go ahead and start to build some of that structure. First of all, we are going to look at g prime of x and use the limit definition of a derivative and say, oh, g prime of x is equal to something that looks like this thing that we find, okay? And then we're going to kind of step back and we're going to look at kind of a second half of the proof that says let's look at what we have in the middle, and what we're actually going to show is that f of x is equal to that thing as well. And so basically g prime is equal to something that's also equal to f, so g prime and f have to be equal to each other. And again, remember what that shows you from the last example is that derivatives and integrals essentially undo each other. Okay, so let's start by looking at the limit definition of the derivative of g. Hopefully you remember what that looks like. The limit as h goes to 0 of g of x plus h minus g of x all over h. This is the limit definition of a derivative. And let's go ahead and plug in our function g from the previous page. Okay, remember g is defined as an integral from a up to x of f of t. So just a thought to remember is that when you're plugging in x plus h, you're thinking about replacing everywhere you have an x with an x plus h. So I'm going to go ahead and write it down here so that I give myself a little bit of space, but this is the limit as h goes to 0 of the integral from a up to, not x, but x plus h. We're replacing an x with an x plus h of f of t dt, and then minus the integral from a up to x of f of t dt. Okay, so here's just another way to rewrite that using the function g that we defined in on the previous page. Okay, now what I want to do is I want to focus on this part right here. Okay, this part has an integral from a up to x plus h, and maybe one of the things you might remember is that we can split that up. We can split up an integral up into 2 separate integrals by adding them together. And so that would look something like this. The limit as h goes to 0 of the integral from a up to x of f of t dt plus the integral from x to x plus h of f of t dt. And then don't forget the minus f of, or minus the other integral over here from a to x of f of t dt. Okay. This is all over h. And if you remember, this part right here basically says that you can talk about the area of from a up to x plus h. You can talk about the whole big area together as one shaded region, or you can split it up into kind of 2 different shaded regions and add them together. So that's kind of where that's coming from. Now notice here we have an integral from a to x of f of t dt right here, canceling with an integral from a up to x of f of t dt right there. One's positive, one's negative. So remember what we were originally talking about is what does g prime of x look like? Well, now g prime of x looks like the limit as h goes to 0 of the integral from x up to x plus h. So the limit as h goes to 0 of the integral from x up to x plus h of f of t dt. And this is all divided by h. Okay. So I tell you what, I'm going to go ahead and just pull that h out front, or the 1 over h out front. This is the limit as h goes to 0 of 1 over h times the integral from x to x plus h of f of t dt. Okay, so remember in kind of the first part I told you that what we were going to do is we were going to say that g prime of x is equal to something, and then f of x equals that same thing. Here is what they're both going to be equal to. That looks pretty complicated and crazy, but we're going to build up this integral part right here by itself when we look at the f of x, and then show that these are both equal. Okay, so we're going to come back to this in just a minute. Let's take a look at just the integral part. Let's look at the integral from x to x plus h of f of t dt. Okay. If you remember from the very first page, I had an integral or an interval from a up to b, and x plus h are somewhere in that interval. And one thing that's really nice is that since f is continuous from a to b, f is actually continuous on the interval from x to x plus h as well. It's continuous everywhere on this whole thing. So I'm going to make a note of this. F is continuous on the interval from x up to x plus h. And you might say, well, why is that useful? Why do we care about that? Well, remember there were 3 different results that we were going to use in our proof here. We haven't actually used any of them yet, so it's time to bring those in. Okay, we have one of our results says that was called the extreme value theorem. So I'll put EVT for extreme value theorem. Remember, the extreme value theorem says that if f is continuous on a closed interval, which it is now over here, this interval from x to x plus h, then f has a maximum and a minimum on that interval. Okay, so because of the extreme value theorem, let me put it this way, there is a u and a v on the interval from x up to x plus h, such that, abbreviate here, such that f of u equals little letter m. Remember from the last video, we had little letter m was talking about the minimum of the function, and f of v was talking about the maximum, capital letter M of the function. And so really what this means is that little letter m is less than or equal to f of t, which is less than or equal to capital letter M for every single value of t that's on that interval. Okay? In other words, there's a lower bound and an upper bound on the function value because the extreme value theorem says you have a maximum and a minimum when you have a function that's continuous on a closed interval. Okay, so that we've used that result. Now the other result that we're going to use, and hopefully this follows pretty directly when we call it a little letter m and a capital letter M, we had a result that says something like, we called it our property number 8 for integrals, and the idea was that if this is true, okay, so since little letter m is less than or equal to f of t, which is less than or equal to capital letter M, let me put it like this, by property number 8, that's what we called it in the last video at least, by property number 8 of integrals, what we have is that this integral then is also bounded. The integral from, or integral of f of t dt, and remember the bounds were from x to x plus h. Now they're bounded by something like this. They're bounded by little letter h times something and capital letter H times something. Now the something in the last video was a b minus a, but that's because the interval went from a up to b. This time they're not bounded by b minus a, or it's not m times b minus a. It's actually b times the upper bound of the interval minus the lower bound of the interval, which is x plus h minus x. In fact, I don't need to write it like that because x plus h minus x is just h. So it's really m times h, and then over here the upper bound is capital letter M times h there as well. So what we've used so far is the extreme value theorem says there's a lower bound and an upper bound on the function, and now we've used this property 8 of integrals that says that the integral is bounded when the function is bounded. Okay, so let's go ahead and take this inequality and let's go ahead and divide both, say both sides, divide everywhere by h. Okay, little letter m is less than or equal to 1 over h times the integral from x up to x plus h of f of t dt, which is less than or equal to capital letter M. Now I will just make a real quick note. We're kind of assuming that h is positive here. If h is negative, everything still works out. We just have to worry about flipping the inequality when you divide by a negative. But since we're kind of assuming that x plus h is further to the right than x, we're assuming that h is positive. Okay, and I tell you what, instead of calling this m and m, let's give it the function value that we had earlier. Little letter m was f of u, and little letter, or capital letter M, was f of v. Now, we've used 2 of our 3 results. The last one we haven't used is one of your favorites, the squeeze theorem. So, we're going to use the squeeze theorem now that we have one thing is less than another is less than another. And so to do that, let's take a look at the limit as h goes to 0 of f of u, and let's take a look at the limit as h goes to 0 of f of v. Because if these both go to the same value, then so does the limit as h goes to 0 of the middle, and that should look really familiar. That's actually what we saw earlier. That's what we've been building up. Okay, so let's take a look at these 2 limits over here. Well, remember what we had was an interval where somewhere over here was a, somewhere over here is b. I'm making the interval bigger to write more in there. Here's an x, and here's an x plus h. And somewhere in between x and x plus h, there's a u and there's a v. So question, what's going to happen as the limit as h goes to 0? Okay, this x plus h is going to get closer and closer and closer and closer and closer to x, and basically this window is just going to shrink and kind of move right towards x. So basically, the limit as h goes to 0 of f of u and the limit as h goes to 0 of f of v, those are both, and it doesn't matter that f is continuous here, that those are both going to equal f of x. Okay, so we get something like this that says f of x is your limit on either end. So let me write this out. So f of x is actually less than or equal to something which is less than or equal to f of x, and what we have is there's something in the middle is the limit as h goes to 0 of this thing. That looks like the limit as h goes to 0 of 1 over h times the integral from x up to x plus h of f of t dt. Does that look familiar, by the way? It should. Okay, so what we just said now is that this whole thing, limit as h goes to 0 of 1 over h times the integral from x up to x plus h of f of t dt, this is actually equal to f of x. But do you remember what this was earlier? Let me go way back. Let me see if I can find that page. Earlier I said we were going to come back to this. The limit as h goes to 0 of 1 over h times the integral from x to x plus h of f of t dt. That was also g prime. It was g prime of x. So what that means is now g prime of x is equal to this big long thing in the middle, and this big long thing in the middle is also equal to f of x. Great. That means that when g of x is defined like we had at the beginning, g of x was the integral from a up to x of f of t dt, what we actually end up getting is that g prime of x is equal to f of t, which is awesome. This is exactly what we wanted because it means now that the derivative here and the integral here kind of undo each other. Oops, I'm sorry, not f of t here, f of x right there. And they kind of undo each other and you get the function that you had in the inside. Okay, this is really, really useful for us to say that integrals and derivatives essentially undo each other. And another way to say that is that an integral is equal to, or is basically the same thing as an antiderivative. Okay, integral equals an antiderivative. Awesome. So this is a proof. It's pretty long, but it's a great one, and it's a really helpful result. I hope you enjoy it. And then in the next video, we'll take a look at part 2 as well as some examples.